Hi guys, welcome back to Data Every Day. Today we'll be looking at a data set of the passenger list for the MS Estonia disaster in 1994. And this is a very tragic disaster in which a ferry carrying 989 passengers crashed in the ocean, and unfortunately over 850 people died. So that's a staggering death rate. I think that's something like 86% of the people. Only 310 of the original 989 were able to reach the decks, and a third of those, almost a third of those, died of hypothermia. So it's a bit of a grim data set, but we're going to try to predict whether or not a passenger survived based on these features. So here's just a graphic that shows what happened to the ship. You can see it listed, and then they tried to perform a 180-degree turn to try to counteract the listing, but it made it worse, and they sunk to the seabed. Alright, so let's start up the notebook. You can see I have written the task for today. Given data about passengers aboard the MS Estonia, let's try to predict if a given passenger survived or not. And we're going to use three models: a logistic regression model, support vector machine, and neural network. And I've written out all the imports we'll need for today's video, which is not too bad. We just have NumPy, pandas, plotly express, and then for preprocessing we have a min-max scaler and train test book function. And we'll be using these three models as listed above. So let's go ahead and import that, and let's load in our data using the pandas read CSV function. And we can get the file path right over here. Here's the CSV we're using. Let's paste it right in, take a look at it, and it's a very simple data set. So this shouldn't be too much of a hassle today. So let's start pre-processing. First, let's see. Okay, let's just hit data.info up here. Let's get a quick count, and we can see there's probably no null values here, right? 9 total, and then everything is non-null. Just to confirm, I'm gonna write data.isNA.sum. You can see we have 0, so we don't have to worry about missing values. But we're gonna worry about encoding these values, because there's not a single numerical column. Actually, age. We only have one numerical column, age. Passenger ID doesn't count. In fact, let's just go ahead and drop passenger ID. Data equals data.drop passenger ID axis 1. Alright. And what else do we not need? Well, okay, well, let's think. First name and last name. Is that going to give us any information? The only thing I can possibly think about what we might get from the name is possibly there's some sort of ordering of the passengers based on alphabetizing. So maybe they were arranged in some order on the ship based on the first letter of their last name. And I'm not sure, but it's good to keep that feature in there just in case. So I think what I'll do is I will just remove first name column. I just don't see how it would give us much useful information. And for the last name column, I'm just going to crop it down to just be the first letter, and then I'll ordinal encode that according to where they came in the alphabet. For country, we can use one-hot encoding. For sex, we'll use binary encoding. And for category, we should check that. Data subcategory dot unique. Here, let's just make encoding. So it only has 2 values, so that also will be binary encoded. And survived is our target column, don't worry about that. Alright, also I want to see how many countries we have. Yeah, a bunch, so we'll use one hot. Alright, so let's do that thing to the last name column, which is pretty simple. Basically, data sub last name dot apply, and the function we're going to apply is going to take in some x, which is a last name, and return x sub 0, which will just be the first letter of the last name. And you can see all of the last names have become letters. So I'm just going to store that in the column, and then I'm going to drop the first name column. Okay. Now let's take a look at our data once again, and now we can worry about encoding. So I'm going to write 3 different functions, one for binary encoding, one for ordinal encoding, and one for one-hot encoding. So binary encode, ordinal encode, and one-hot encode. Alright. And basically, I'm going to write the same thing in each to start. Let me just, here, we're going to make a, okay, each one's going to take a data frame, and it's going to take, sorry, one sec, so I get this, and it's going to take a column. Right, so this will be the data frame we want to change and the column of that data frame that we'd like to encode. And one hot, that's all it needs. For ordinal, we also have to specify an ordering that we want to, like we have to sort the list of values in the column so it knows how to order them. And for binary encode, we'll specify a positive value. And we're just going to start by making a copy of the data frame. And we'll end by returning the data frame. Now, for binary encode, we're going to apply a lambda function that's going to take in an x, which would be, for example, in the sex category, we'd have M or F. So it's going to take in one of these letters, and then it's going to return 1 if x is the positive value that we specified, and otherwise 0. So M will go to 1, F will go to 0, F will go to 0, M will go to 1, F will go to 0, like that. For ordinal encode, this will be, for example, the last name, A through Z, will get mapped to 0 through 25. And for this, we will also apply a lambda function. Oh, I also realized I have to actually set this. Okay. And this too. But we're going to apply a lambda function here that's going to take in an x, which would be one of these letters. And we're going to return that letter indexed in the ordering. So if our ordering is a list of alphabet letters, A through Z, if we take the, oh sorry, not indexed, index. If we take the index of x in that list of letters, so for example, if x is Z, it'll find the index of it in the alphabet, which would be 25, and so Z will become 25. A will become 0, and so on. Alright, so that's it for this one. And then for one hot, we're going to do, I think, 3 lines of code here. One will be to create a dummies data frame using pandas.getDummies, which will take in the column, df subcolumn. Then we're going to set the data frame equal to the concatenation of the old data frame and this new dummies thing on the column axis. And then we're just going to drop the original column from which we created the dummies. And yeah, so these are our encoding functions. And with those, we can now specify the ordering and the positive value. Well, the ordering we should write alphabet ordering. This can just be a string since we can iterate through a string, right? We can index on a string as well. So A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. S, T, U. Okay. Looks good to me. Alright, so did I get it right? P, Q, R, S, T, U. There's an R in there. I knew something was wrong. Okay. Now we will encode. So run that. Now we're going to separate them into three categories: the binary encodes, ordinal encodes, and one-hot encodes. So first binary we'll do, which would be sex and category, right? Because we saw category only had two values. So data sub sex equals binary encode data sex. And then we specify the positive label, which will be M by convention. Then we'll do another binary encode for category. And put it in here. And then we will ordinal encode. Oh, and I realized actually we're not setting the columns, we set the actual data frame as it returns a DF. Okay. Then ordinal encode. The category we're ordinal encoding is the last name. And the ordering is going to be alphabet ordering. Alright, and last will just be the one-hot encode, which will be the country. Alright, we run that. Take a look at our data. You can see we now have 21 columns and everything is in numerical form. Fantastic. So now we can do splitting and scaling. So we'll split into Y and X. Y will be our survived column, which is what we're trying to predict. And X is going to be everything except the survived column. Then we're going to create a scalar, which will be the min-max scalar from sklearn. That will scale all the values to have a range between 0 and 1. And this works well because we don't have probably not really any outliers, and many of the values are already between 0 and 1. So X equals scalar dot fit transform X, and so we scaled X, and then we'd like to split it again into a train and test set. So X train X test, Y train Y test is equal to train test split. That's the function from sklearn. It takes in a Y, an X, a Y, and a train size, which we'll say is 70%. Alright, run that. And now we have these 4 different subsets of our data that we can use to train. Okay, so we're using these 3 models, right? Logistic regression, support vector machine, and neural network. And we're going to compare their performances. So how about I create the logistic model as log model equals logistic regression. The SVM model will be SVC, and we specify a inverse regularization strength here. We just set it to 1.0. I think that's the default. And then ANN model will be the MLP classifier, for which we have to specify the sizes of the hidden layers, which we'll just make it 16 by 16. Alright, then we'll fit them to our data. So model.fit xtrain ytrain, and we can run that. Alright, then we're going to do one more thing. Okay, because so many people died, because it has a death rate of like 86%, right? It says right here, since the death toll is well above 80%, can you make a classifier that beats the baseline, which is all passengers died? Right? Because if we predict no, y equals 0 for all the passengers, we still get an accuracy of 86%, because the only ones we get wrong are the 14% left over that actually survived. So accuracy isn't going to be our best kind of metric in this case. We can use it, and if it's well above 86%, then we know maybe we're doing something right. But we shouldn't think, like, we get 86% accuracy, it doesn't mean our model's doing well. In fact, it could be doing very badly. It could just be saying everyone died, which isn't true. We want a better metric, and a better metric we can use, which I'll actually import up here, will be the ROC AUC score, Receiver Operating Characteristic Curve, area under the curve. So from sklearn.metrics, import ROC AUC score. And I'm going to get that score for each one of them. So I'm going to say log svm ann, and then I'm going to do this 3 times. Alright, so first I'm going to get the predictions. Well, first I'll get the accuracy scores. Log ac for accuracy is going to be equal to I'll fill that in a sec. Something model dot score, which just by default returns the accuracies of the model evaluated on X test and Y test. And so here we have log, here we have svm, here we have ann. Now for here, we're going to say log predictions, or preds, is going to be blank model dot predict on the test set X. And here will be log, here will be svm, here will be ann. And for these ones, this will be the ROC AUC, so I'll say AUC equals something model dot, no, actually no, we do ROC AUC score, that's what we imported, of the true values, Y test, and the false, the predicted values, which will be preds. And so this here is log svm and ann. Alright, we run that, and now we can create a let's create some bar graphs to see how our models performed in these two ways. So we'll make a bar graph using Plotly Express. So px.bar, let's say fig equals px.bar, and then we'll say accuracy fig. X equals, so this will be our labels on the X, so this will just be the names of the 3 models. Logistic Regression, support vector machine, and neural network. For our y, this will be the actual scores, log ac, svm ac, ann ac. Then our labels, on the x, this is the label axes, x will be model, and y will be accuracy. Then color, this is just going to make it a little prettier. We'll just be the same as the x. So we have a legend on the side. Then our title will be, we'll say model accuracy. Alright, and before I show that one, I'm just going to do the same thing but for the AUC figure. So these will be AUC, and this will be rock AUC, and then model rock AUC. Alright, and then we'll say accuracy fig.show and AUC fig.show. Alright, let's see how we did. So for our accuracies, this is pretty much what we expected, right? It looks like our support vector machine did the best here with an accuracy of 85.5%. This one had 84.8%, and this one has 84.2%. So I think that's about the we can actually check. Let's check exactly. Y is going to be the true values of who survived, and 1 means they survived. So if we get the sum, if we sum across it, we'll get the total number of people who survived, right? And then if we divide that by the length of y, we'll get the percentage of people that survived. And if we say 1 minus that, we'll get the percentage of people who died. And it's 86. So these models are actually worse than the baseline, right? At least in terms of the accuracy here. Looks like this is doing worse than just saying everyone died. Now let's take a look at the AUC. So here, alright, we can see we have AUCs of 0.5. So that's not so good. I mean, it's not the worst. If we got everything wrong, we have an AUC of 0, and if we got everything right, we'd have an AUC of 1. So this is right in the middle, 0.5. And interesting. I mean, we may have made a mistake, but it's also possible that this data just, it doesn't have very much information that would lead to an accurate prediction about whether or not a given passenger survived. But this is what we got, and I think that will sum up today's video. Thank you so much for watching. If you enjoyed, make sure to subscribe and hit the bell, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.